Hello and welcome to Physics Teacher. In this live session, I'm going to be going over the acid-base equilibrium unit for the grade 12 chemistry class. I'm going to be going over some words, some important words that might appear on my students' test tomorrow, some communication type questions, and I have two problems that we'll be going over. If you need more problems and more practice, I did release a tutorial a couple days ago on this unit, which has about 6 problems that I go through. So you can skim through that as well. So let's start with the word list. Okay. At any time, if anyone has any questions, just let me know in the chat. And if you know any of these words, let me know those as well. So let's start with our first one. If anyone knows this, let me know. So blank is an acid with more than one ionizable hydrogen. Okay. This is going to be polyprotic. All right. So oh, that was supposed to be a P. Polyprotic. All right. Next one down. Weak acids do not blank completely in aqueous solutions. So they do not ionize completely. So that was what? 5 down. Ionize. Okay. Yes, we're doing crosswords. I mean, it might help. You are going to have quite a few fill in the blanks on tomorrow's test. Just saying. Okay, continuing. Across, number 1. The indicator blank turns pink in a... Oh, I can't even spell this. Let's go to the next one. Number 3, we'll save that one for the end. The pollutant blank. If anyone knows how to spell phenolphthalein, go ahead, give it a shot in the chat. The pollutant blank contributes to acid rain. Okay, that'll be sulfur trioxide. Okay, so number 3, sulfur trioxide. And I talk about this pollutant, how it affects acid rains, is one of the examples in the tutorial that I left a couple days ago. Next, water is considered blank since it can function as a Bronsted-Lowry acid or base. What's that called? Do we remember? Anyone? Let me see the chat here. Do you have any videos on grade 11 solutions? Yes, I do. Just go to my channel, go to my playlist, and I have lots of tutorials for grade 11 chemistry, and you'll find some in the solutions unit as well. All right, so continuing. Amphoteric. Okay, amphoteric. Number 4. This one I think I can spell. Teric. Okay, couple more to go. A color change determines the blank of an acid-base titration. My students should know this. You did a titration recently. What's that endpoint called? Come on, I just said it. It's endpoint. Endpoint. There we go. Endpoint. Now, let's give this phenolphthalein a shot here. Null. Oh, next one's going to be a P. I think it's a pH because we always just write it as pH. And then I think it's THAL. Looks like that fits. Well, whether it's spelled right or not, it fits. All right. Let's move on. This one. This is a great type of explanation question. Explain why sodium carbonate produces a basic solution when dissolved in water. Okay, so what do we know? Well, sodium hydroxide is a strong base, and carbonic acid is a weak acid. Now, sodium carbonate is a basic salt derived from the neutralization reaction between sodium hydroxide and carbonic acid. And so that salt, sodium carbonate, is Na2CO3. Now when we split this up into its ions, because it's going to dissociate, it's a salt, it's going to dissociate in a solution, we're going to have Na plus 1, we're going to need 2 of those, balance it, and carbonate minus 2. Now the sodium we're not really too interested in, but the carbonate we are. Okay, so the carbonate is our anion of a weak acid, and when we have collisions with water molecules, so this is aqueous, I should be writing my states here. This is liquid. What's going to happen is it's going to steal one of those protons. So we're going to get HCO3 -1 plus, look at this, hydroxide. Okay, so it forms a base. Right? So the anion of a weak acid forms a base. Cool. All right. Just make sure you explain all that on a test. You can't just talk into a microphone. You'll have to write it down. Sorry. Any questions? All right, let's keep going. Here's a nice basic one. Calculate the pH of a 0.7 liter solution containing 1.2 grams of benzoic acid. All right, so let's start by writing the equation. So we have benzoic acid, C6H5COOH, aqueous, plus we're going to have H2O, liquid, and this is a weak acid, so it's going to be in equilibrium. One of those hydrogens is going to go to the water, so we get hydronium. And we're left with our benzoate ion. So C6H5COO negative. And I realize my head is covering that up. Yeah, sorry about that. My head is covering it up. But it's just a benzoate ion. Okay, we're not too interested in that one anyways. So, moving on, we are given the mass of benzoic acid. So what I want is the concentration. So just on the side here, let's figure out the concentration. This is a two-step process. First, we're going to figure out how many moles we have. So moles is just going to be mass, so 1.2 grams, divided by molar mass. And so for benzoic acid, it's 122 grams per mole. You guys can just check that up on your periodic table if you need to. So that gives us 9.8 times 10 to the minus 3 moles. We want a concentration though. Concentration is moles per volume. So we got moles, 9.8 times 10 to the minus 3 moles over 0.7 liters. So we get a concentration of 0.014 moles per liter. Okay, that's done. Now we need to set up our equilibrium law. Because to figure out the pH, we need to know the concentration of hydronium. To figure out the concentration of hydronium, we can't just simply use stoichiometry because this is an equilibrium reaction. It doesn't go to completion. So we're going to need to use our equilibrium law. So let's use an ice chart. So ice chart is just your concentrations of what you start off with, what changes, and what you end up having at equilibrium. So for benzoic acid, we start off with, we just calculated that, 0.014. Initially, we don't start off with any hydronium or benzoate ions. And we don't need to worry about the water. That's a liquid. It's going to get encompassed with the equilibrium constant. Okay. Well, what's going to change? Well, it's already balanced, so the ratios are all 1 to 1. So hydronium will change by some value, positive x. This anion will do the same thing. And then we have negative x. So we're going to lose some of that benzoic acid to produce some of the hydronium and benzoate ions. So what are our concentrations at equilibrium? So for the acid, we have 0.014 minus x. And then over here, we just have x and x. Okay. So now we set up our equilibrium equation. So Ka is going to equal, this is always hard to say, but it is the product of the products. The product of the concentrations for the products of the products. So we have our hydronium concentration and our benzoate H, 5COO negative, all over. I'm running out of room, but our acid. So C6H5COOH. Okay, I'm just going to write this to the side and then I'll make some room. So that's x times x, so we have x squared all over 0.014 minus x. Okay, let me make some room here. Get rid of the ice chart, we don't need it anymore. We've created our equilibrium law equation, and now we just need to solve that. All right, so you can look up the acid constant. Okay, for benzoic acid, it is 6.5 times 10 to the minus 5. And that's going to equal our x squared over 0.014 minus x. Now, if you want to go ahead and solve that, it looks like it's going to be a quadratic, so that's a little bit messy. But the question is, to make it simpler, can I drop the x? Does it have a big effect if I were to do that? Now, we can calculate that. So what we're going to do is, if the concentration of that initial acid divided by that Ka value is greater than or equal to 100, then it's okay to drop the x. It's not going to have much of an influence on our final answer. So the concentration of the initial acid, we already figured that out. Right? It's right there. So 0.014 divided by our Ka value, 6.5 times 10 to the minus 5. So if we do that, it's about 215. So yeah, it's definitely greater than 100, so we can drop that x. Now it becomes very simple to solve. We don't have to solve a quadratic equation. So multiply both sides by 0.014. So, and we've got 0.014 times that Ka value. And that is going to equal x squared. But take the square root of both sides and we can solve for x. So when we do that, we get x equal to 9.5 times 10 to the minus 4 moles per liter. I erased the ice chart, but if you remember on the ice chart, x is also the concentration of our hydronium atoms. So we're almost done. Now that we have that, get this eraser here. Now that we have the concentration of hydronium atoms, we can figure out the pH. So our pH is equal to negative log of our concentration of hydronium, which we determined as 9.5 times 10 to the minus 4. So we plug that into our calculators and we get a pH of 3.0. Not so bad. Be a fairly nice question beginning of a test just to get your feet wet. But the question I like is very similar to this, but it's the opposite. Students freak out when you do the opposite. But this one gives you how many grams of benzoic acid and asks for the pH. What if it gave you the pH and asked you for how many grams of an acid? That's what we're going to do next. Did anyone have any questions with that last one? No? Okay. Just plow forward. Okay. So determine the mass of acetic acid in 2 liters if the pH is 3.52. So let's start off with our equation. Maybe write a little bit lower so my head doesn't get in the way. So we have acetic acid, CH3, COOH, aqueous, plus it's going to collide with those water molecules, and water is going to steal a proton to make hydronium, and then we're left with acetate ions, CH3COO negative. All right, so there's our equation. Now we don't start off the mass, we start off with the pH. So the pH is 3.52. What can I get from this value? And we can actually get the concentration of hydronium. See how we're going backwards? So if we do that, we can figure out the concentration of hydronium is equal to 10 to the power of negative pH. So if we plug this into our calculator, we get that concentration to be 3.02 times 10 to the minus 4 moles per liter. All right. What we want to know is the concentration of the original acid, because then we'll work backwards to figure out how many moles and then what the mass is. To do that, again, equilibrium law. So Ka is going to equal the concentrations of the products of the product. No, the concentrations of the product of the products. There you go, I put the S in the wrong place. Okay, so we have H3O times by acetate I know most of them you don't even have to balance, but because they already are, but always just double check just in case, because I find students will often miss like a square on the concentration or something. But in this case, we're good. All right. So what am I going to put in here? Let's just do a mini ice chart here. So I, C, and E. So for acid, what do we start off with? I don't know what we start off with. That's what I'm trying to figure out. So let's call that X. Hydronium, nothing. Acetate, nothing. Okay. Then what's the change? I don't quite know, but I do know the concentration of hydronium at equilibrium. So down here, that's going to be 3.02 times 10 to the minus 4. How did it go from 0 to that? Well, I must have added 3.02 times 10 to the minus 4. So I do know the change. And due to the molar ratios all being 1-to-1, this is also going to be plus 3.02, although I'm not interested in the anion at all. Let's just write it down, which is going to end up with the same. Now the X is what's interesting. So the change here will be minus 3.02, because it'll be initially a forward reaction to equilibrium times 10 to the minus 4. So at equilibrium, we have X minus 3.02 times 10 to the minus 4. All right, so now we know what to throw into our equilibrium law. Right? We have those equilibrium concentrations. So let's do that. Make a little space here. So the Ka value for acetic acid is 1.8 times 10 to the minus 5. Hydronium and acetate, we have the same concentration, so let's just square it. So 3.02 times 10 to the minus 4, and square that. And then we're going to divide by x minus 3.02 times 10 to the minus 4. Now, again, that's a little bit messy to solve. The question is, can I cancel this out? Now, what we'd have to do is take the concentration of the acid, which is x, and divide by Ka to see if that ratio is greater than 100. The problem is, I don't know what x is, so I can't figure it out. But you know what? Let's just wing it. Let's say it works. We are going to have to check when we finish solving to make sure it did actually work. And if it doesn't, we're just going to have to come back and redo it without canceling that. So let's hope it works. I'll make myself some room. Let's get rid of this ice chart, since we've subbed everything in. X is what we're looking for, because that is our original concentration of acetic acid. So, we could just cross multiply these, right? Which will give us x equals 3.02 times 10 to the minus 4 squared all over 1.8 times 10 to the minus 5. How's everyone doing? No questions? Okay. So, plug this into our calculator. And we get 5.1 times 10 to the minus 3 moles per liter. So now the question is, was it okay to cross that out? You always have to show your check, right? On a test, show your check. Okay, so our check, here's what we're going to do, our little check. Take the concentration of that acid. So this is the concentration of our original acetic acid, because that's X. So take that, 5.1 times 10 to the minus 3. Divide that by your Ka value, 1.8 times 10 to the minus 5. Is that greater than 100? It is about, oh, thank goodness, 283. Okay, so we're good. So it is definitely greater than or equal to 100. So our check pans out. Now we have the concentration of acetic acid. Stepping backwards, concentration is moles per volume. So if we wanted to calculate moles, that is going to be concentration times volume. We know the volume, it's in the question, and we just did a lot of work to find the concentration. So 5.1 times 10 to the minus 3 moles per liter times by 2 liters gives us the number of moles. 1.02 times 10 to the minus 2 moles. Okay. Where am I going to solve for mass? I need to erase something. Let's make some room. So we have the number of moles. So now we just have to solve for mass. So moles equals mass over molar mass, or rearranging, mass is equal to moles times molar mass. So we got our number of moles, 1.02 times 10 to the minus 2 moles. Our molar mass of acetic acid is about 60.1 grams per mole. which gives us a final mass of 0.61 grams of that original acetic acid. I love that backwards question. It's a good question. Okay. All right. Anyone else have any questions? How do I? Nope. I'm not seeing any questions. Last chance. 3, 2, 1. All right. Well, to all my students, good luck on your test tomorrow. And thanks for watching.